Hello, my name is Ivory Scherphorn. Um, I am in class CSC 575, and this is my presentation for Module 2. So the 575 problem was given an array of n players, where each player has a preference for exactly one of the three roles, attacker, defender, or healer. Return one of the largest possible sets of legal teams of players and their legal role assignments. In a legal solution, there can be two team compositions. There can be one defender, D, one healer, H, and three attackers, A. Or four healers and one attacker. In a legal solution, each player assigned to a team must be assigned to exactly one role, and it must be their preferred role, so they can't change roles. A defender cannot suddenly become an attacker. So in a legal solution, there can be at most n uh, over 5 teams, which makes sense because say there was 25 players and you can make teams of 5. Understandable. So in my example instance, I used 28 players, 6 defenders, 10 healers, and 12 attackers. The max available teams from that is either group 1 that has 8 players left over, 4 groups of team composition 1. So 1 defender, 1 healer, 3 attackers. Or group 2, which also has 8 players left over, 2 of composition team 1 and 2 of composition team 2. Now both of these are equal because the optimality that we're asking for is just the most teams that can be returned, and the least amount of players left over, which go hand in hand. So I created an algorithm that tries to do one of these. So for my algorithm, I found it best to change the player types from characters to integers. So D, defender, equals 10, healer equals 4, and attacker equals 1. I picked these numbers because if you can make team 1, team composition 1, and team composition 2, they both equal 17. Because 10, 14, 17, 16, 17. So to make sure that only these two compositions, team compositions, can be returned, the teams have to equal 17. This makes sure that there cannot be, one healer and 4 attackers returned, or 3 defenders and 2 healers returned. It has to equal 17. So I took elements from the greedy algorithm because my algorithm that I came up with only cares really for local optimality, doesn't really care too much about global optimality until the end, where it puts all local optimalities that were found together. So for example, if in a given array at index 0, there's a D defender. So it'll check, can H be added? Yes. Can A be added? Yes. Can D be added? No. Can A be added? Yes. And then in my algorithm, these players would be no longer available to use, and they'll go to the next available player to check again. So it's just, it's not saving them per se, in a way to make it more optimal, to make it faster. It's just trying to find the local optimality in the given index, available index of a player. But again, the teams have to equal to 17. So that's how we can skip. If it was a D, it can't be another D because it'd be 10 and 10, that's 20, and so on. So my pseudocode is assuming that array is given in random order. So my function is called team sort. It takes an int array or 3 int arrays, The first int array is the original array of players. So, 10, 4, 1, 1, 1, 4, 1, 1, 10, blah, 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 until 28 players, as long as still within, 6 defenders, 10 healers, and 12 attackers. Array 2 is used to check if the players have already been used. Array 3 is the final returned array that has all the documented players that we could use along with the teams. And it's just the length of the array, it's just a counter. So it does make 2 arrays with lengths of 5 or 5 indexes. So a sorted team, and this is where we will put the actual sorted teams, not the indexes, just the team. So 10, 4, 1, 1, 1, or 4 4s and 1 1. And this indexes array takes the corresponding index where we found those numbers. So 10 could have been found at index 3 in the original array that we iterate through. And then the next one, index, and the indexes array at index 2 could be a 7, because that's where we found the 4 that fits, and so on. So we have sum equals 0, j equals 0, and j is the iterator for the sorted team array and also for the indexes team array, but we'll see how that works. So while j is less than 5, because there's only teams of 5, they cannot be less than or greater than 5. And if n equals 4, it will break because there's only teams of 5, like I just said. So if there's only n equals 4 players left, there's only 4 players left to check. It doesn't matter, we can't make a team that's not enough players. So it automatically breaks. But while j is less than 5, there will be a for loop. It has an if else statement embedded in it. So from I to array length, which is array is the original set of players, the random, 10, 4, and 1 set of players. If array 2, which is the checking array, at index I is greater than 0, then continue on because we've used it. So, array 2, when it's first initialized, all the indexes will equal 0. And we'll see later on how if it has been used that we change that index to be greater than 0 to keep track that we've already used that one, because array 2 is the same length as the original player array as well. So that's how we can check the corresponding indexes of array and array 2. They're the same. Else, meaning that at array 2 at I was 0, else, if array at I plus sum is less than or equal to 17, they'll take the element at array I and put into sorted team at index j. And then it will add that index element to sum, and that becomes the new sum. So it'll keep checking in this for loop the sum. And as long as the sum is less than 17, it'll keep being put into the sorted team array. So again, this makes sure that if there's 2 defenders, it's not possible because the defender, if from this algorithm, equals 10. So 10 and 10 is 20, it won't work. So it won't be added to the sorted team. But 10 and 4 will work, 10 and 1 will work, and so on and so forth. And we also keep track of where that index was found of the usable player. So it uses in I and put into the indexes array. We keep track of the indexes at j. So j and sorted team, since they are both 5, they are always incrementing together. Because if we find one, it needs to go in the sorted team, and the index of I of that element needs to go into the indexes array. And then j plus plus. because we need to get it. J needs to be less than 5, so it needs to iterate through. So now this part is if the sum is 17, is exactly 17, which is what we want. Team composition 1 and team composition 2 both equal 17. So if sum equals 17, and this is after team the teams have been sorted through, it'll go to the indexes array and iterate through until index array length -1. Now put the elements that are in the indexes array into 0. Now this 0 is just to help me keep track of what indexes are going to be used in array 2. So for example, say that the indexes at the indexes array at 1, so k equals 1, is 5. It'll go into 0, which is now assigned 5. Now at array 2 at index 5, it'll be 5 plus 1, which is 6. And this just helps me visually keep track of how many I've used rather than having to do a +1 in my head every time I look at an index because the arrays start at index 0. So that's if sum equals 17. Now this P is an iterator for the sorted team. So this for loop is to keep track of each player that has been used, that has created a successful team, and puts it in array 3 to be outputted. So from R to array 3 dot length -1, so array length -1. If similar to before, if array 3 at R is greater than 0, continue. Because if it's greater than 0, that means it's already been assigned. It already has been documented that that index has been used. So just keep moving on until we find an index that equals 0, which indicates it hasn't been used yet. And this is to make sure all the teams stay in order. You know, so if we find a team, say it's team composition 1, it'll be at index 0, 10, index 1, 4, index 2, 3, 4, 1s, because it's 10, 4, 1, 1 for that team composition. So it's to make sure that it can't go to 10 and then at index 0 and then 4 at index 8. I want them in order. And especially as this recursively calls, I don't want it to accidentally do the same first 5 indexes, so 0 through 4, and it's not really documenting the appropriate data. It's not a good reflection of what's actually happening. So that's to make sure that this iterates through properly, so we can keep track of all the available teams that we can use. So this P goes through the sorted team because we're keeping the elements of this. I'm not worried about the indexes anymore. I'm worried about the elements. So, you know, team composition 1 and team composition 2. So it goes into player, and then player is assigned to array 3, which again is the array that'll be returned to show all the players and team compositions that we can use. Put plus plus to iterate through, and n minus minus. This is where the counter comes in. So each time a player is used, we will subtract 1 from n. And the idea is that it's supposed to represent that one player has been used through a counter. So If we were able to make a team of 5, then it would be n minus minus 5 times. So say we start at 28, which is the beginning, the first time we run this program, this will now have n equal to 23. And recursively call it, and it'll keep iterating through. And if it was a best case scenario, we could iterate through all of them. Like I said earlier, if it was 25 for the array length and we have 5 teams, it'd be perfect. But sometimes it's not perfect. So if sum is not 17, so it's less than 17, because we already checked to make sure it can't be greater than 17. If sum is not 17, then we need to assign the first element's index to 0 and place that in array 2 to show that we can't use that player anymore. So say in one team composition, it was 10 and 4 ones, doesn't equal 17. So at indexes where the 10 was, say that was like 4, it will go into 0. And then the same thing, similar to before, 0 plus 1, it'll still go into array 2 at index 4, but it'll say 5. Again, just easier for me to keep track of when I look at it, what has been used and where. And then, n minus minus only once, because I'm only documenting this one player that I can't be used anymore, that I can't use anymore. And then recursion call again, same, and then it returns array 3, which again is the final array that has all the possible teams and all the possible players. So my pseudocode, which probably is slightly easier to read with all the notes, is mostly, orange is time complexity and blue is space complexity. So time complexity, space complexity. So for time complexity, most of it is constant time. There is n for the while loop, big O of n for the array in the worst case, but only O of 5 for the best case. And then constant, until this for loop, which is O of n, big O of n. Same thing for this for loop, big O of n. And then for best case scenario here, so that's if sum is 17, then it will be the time complexity for the recursive call will be t minus 9 at best. And the idea behind that is if we have a team of 5, then we are doing n minus minus 5 times. And then it can only go to 4, because if there are 4 players left, we can't make a team. So n minus 4 minus 5 is n minus 9. So at best, time complexity can be t n minus 9. But that recursive call also just takes a space of a big O of n, because nothing is being gotten rid of. It's still using all of it. So for the space complexity, is big O of n for the 2 integer arrays, and the rest is constant until we get to these for loops here. So the for loop is big O of n. This for loop is also big O of n, because it just holds all of n's. And then this is the worst case scenario. For time complexity, it would be t n minus 5, because again, we're only doing one n minus minus one time, because we're signifying that only one player has been used and it can only go down to 4 because when n equals 4, it's going to stop. So n minus 1 minus 4 is n minus 5. That also still has a space complexity of big O of n because it holds, nothing is being changed, it's still holding everything in the stack. And then return array 3, which is just constant time. So the time complexity for the best is all of this, which comes down to t of n equals t of n minus 9. Again, that's the minus 5 for the 5 players used and the minus 4 because n can only go to 4, plus 3n plus 33. But 3n plus 33 has constants, so it becomes t of n equals t of n minus 9 plus n. If we do recursion tree, you can see that we do t of n is the starting point, then n, t of n minus 9, then n minus 9. We're minusing 9 on both sides. Minus 9, t of n minus 18, n minus 18, t of n minus 27. And if you were to keep going, if n was a very, very large number, you would see that eventually this would become t of n equals n times n plus 1 over 2, which is a complexity of O of n squared. So still pretty high, despite using some arrays, but it mostly works. So, but the worst case time complexity is about the same because it's just a constant difference. So it's t of n equals t of n minus 5 plus 2 of n plus 25. But again, these are constants, so t of n minus 5 plus n. And we do the same recursion tree just about. But again, the n minus 5 is, the minus 5 is a constant. So it still comes out to t of n equals n times n plus 1 over 2, which is still O of n squared. The space complexity for best is 4n plus 33. So that comes out to just n because we get rid of the constants. And the same for worst case, it's just a different constant, so it's 3n plus 25. So still space complexity of theta of n for both. Now this is my Java code. It's very, very similar to my pseudocode. It takes in, for the main method, however, we do need to take in an array of players, random order, create a 0 array. This is array 2 to check to make sure that player has been used or not. The final team is the returned array 3 that shows the list of teams that were used and their players. And, is the length of the players. And this new int team is just so we can print out this final array. So my function, team sort takes an int array by 3 int arrays. Int array is the players. Int array 2 is the 0 array here, the checking array. And int array 3 is the final team, the returned array, and int n is just the counter. So it still takes, still creates 2 arrays with a length of 5, still does the while loop that will break if n equals 4. No, it's just about the same as my pseudocode. So it'll do this loop to check to make sure that array 2 has a player that has, at that index, the player has not been used. If it has not been used, and if it's less than 17, it'll be added to the sorted team array. And their indexes will be added to the index array. And then if the sum at the end of that equals 17, then it will put those indexes into array 2 to keep track that we have used those team players, those players. This for loop puts those players in the final array to be returned. Recursive, we call it. And if sum is less than 17 or greater than 17, then the first index at array indexes, the first index at the array indexes, so index 0, will be put into the array 2 to show that we cannot use that player again. We've already tried and it doesn't work. Then n minus minus for that one player. Oh, and then n minus minus for 4 here for the 5 players that were possibly able to be used. And n minus minus again here for the 1 player that couldn't be used, but we don't want to repeat using, and then returns array 3, which is the final array to show what team compositions were available and could be used. So in my experiments, which I did over about 50 times, I used the same player composition. So 6 defenders, 10 healers, and 12 attackers. So an array length of 28. I just mixed the order. So sometimes it was descending, sometimes it was ascending, sometimes it was started with a 4. Sometimes it started with like a healer, started with a 1 attacker, started with a 10 a defender, and just mix them up to make sure that it could work almost every time, or hopefully every time. It did not work every time. It worked most times though. All successful outputs, however, do indeed show the most optimal team availability within that array. At least one of them. So remember, it was group 1 that was 4 of team composition 1, or group 2 that was 2 of team composition 1 and 2 of team composition 2. So it showed one of those each time. But I found that when the algorithm didn't work, it was due to an exception that I couldn't quite figure out. So here are the output successes. See, using different orders in the array, they were able to output, in this case, group 1, which was the 4 team 1 composition. So defender, healer, and 3 attackers. So there's 4 present. There's right here 10, 4, 1, 1, 1 team, 10, 4, 1, 1, 2 teams, 10, 4, 4, 10, 4, 1, 1, 1, 3 teams, and 10, 4, 1, 1, 1, 4 teams. So these are the 4 teams that can be made from this composition, or this array, excuse me. And they have 8 players left over, and that falls into group 1, like I said earlier, so it's still optimal. And the other outputs do the exact same, despite the difference in composition, difference in order. Where it failed were array compositions like this. Kept saying that index 5 was all bounds for length 5. So there were times where it didn't work. It's not 100% foolproof algorithm, but it does mostly work, usually works. So the benefits of my algorithm is that it does mostly work even in unsorted arrays, normally. And if the output is successful, it always outputs the optimal number of teams with the least number of players left over. It works best in sorted arrays of descending order, because if we start with 1s, groups of 1s, and then groups of 4s and groups of 10s, it's going to keep checking every single index that has 1, which are back to back, and that slows down the process. So it's better to have the array in descending order, because if we have 5 1s, it's just 5, it's too small. But if we have a 10, we have a possibility for 3 1s and a 4. So it makes things slightly faster. It does have a slightly lower time complexity than it could have had, because of some simple loop for array insertion, but it still has an n² time complexity. The limitations of this program is that it doesn't work for all unsorted arrays, as we saw. Sometimes it does fail. It still has a higher time complexity, and squared is still pretty high time complexity. And it doesn't work well, like I just explained, for arrays in ascending order. It works best for arrays in descending order. It uses higher space complexity due to several arrays. I believe I used 5 arrays um, to complete this algorithm. So it's still pretty high for a higher time complex or space complexity, but big O then or theta then, it's not bad. It does have a high preference for team 1 team creation, so the defender, healer, and 3 attackers. Again, like I said, um, it's because though 10 is a higher number, it leaves less numbers that could possibly be used. If we start with a 1, there's lots of numbers, almost every number could be used. And 4 is very similar, a little less so though. So it does tend to, just like you saw in my outputs, to have a preference for team 1 composition over team 2 composition. But again, in this case, the team 1, group 1 composition, which was 4 of team 1, and the group 2 composition, which was 2 of team 1 and 2 of team 2, were the same optimality wise. They were both 4 teams and they both had 8 players left over. So I'm successful in that regard. So that's the end of my presentation. If you have any questions, please let me know. And I hope you guys have a great day.